Welcome everybody to Algebra 2, Unit 10, Section 1. And Unit 10 is going to be about rational functions. Section 1, we're learning how to graph simple rational functions. So to warm up, we want to know what do the graphs x equals 5 and y equal 2 look like? One is horizontal and one is vertical, but which one's which? Well, x is 5. X equals 5 means the x value is never changing. So it's never going left and right. Instead, it's just going up and down. So it's vertical. Meaning y equals 2 means y is always 2. It's never going up and down. It's just going left to right, meaning it is horizontal. Rational functions. A rational function has the form f of x is equal to some p of x divided by another q of x. And this is where both p of x and q of x are polynomials and q of x doesn't equal 0, because that would mean you divide by 0. The parent function is f of x equals 1 over x. That's the most simple rational function you can have, where the top polynomial is just 1, because that is still a polynomial, and the bottom polynomial is x. This graph forms what we call a hyperbola, and it consists of two branches. That's what a hyperbola means. And so if we draw this graph here, it looks something like this. Knowing mine's not perfect, like for example, this down here wouldn't have this little stretch where it goes up. It would actually just go slightly down over time. And so these sections of the graph never touch. And the reason that is because this graph has what we call vertical asymptotes. So it has vertical asymptotes that the function, the graph, will never cross. And it can also have end behavior, or also known as horizontal asymptotes. The end arrows get close to. All right, so how to find things in this? Okay, so how to find the x-intercepts, where y equals 0? Well, you set y equal to 0. And then you solve for x. And similarly, to find the y-intercepts, you set x equal to 0 and solve for y. If you recall before, back when we did quadratics or when we did linear functions, we said, hey, whenever you have the x-intercept or the y-intercept, the other variable, the other value is always 0. So to find vertical asymptotes, this one's new, we set the denominator equal to 0 and solve. Now, for end behavior asymptotes, you compare the degree of the numerator, and we'll call the degree of the numerator n, to the degree of the denominator, and we'll call the degree of the denominator d. So when you compare the degree of each of them, I'm saying the highest exponent really of those, when the degrees are equal, then you have a horizontal asymptote at y equaling the leading coefficient. Plus whatever translation is occurring up or down. When you have the numerator is greater, the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. Instead, there is sometimes a slant asymptote. We won't get into when there's a slant, what that looks like in Algebra 2. We won't concern ourselves with that. That'll be more of a pre-calculus college algebra endeavor. Now, if the degree of the numerator is less than the degree of the denominator, then there's a horizontal asymptote when y equals 0, plus whatever translation up or down there is. You might recall that vertical translations take place after everything else. So this would be like f of x equals p of x over q of x. And then the vertical translation would be this part, like plus 5 or minus 2. And those would be translating the whole graph up 5 or down 2, respectively. All right, so now let's put this into practice a little bit. On examples 1, A, B, and C here, we're going to identify the end behavior and the vertical asymptotes of the following functions. So on example A, first finding the vertical asymptotes. So we set the denominator equal to 0. So 5x plus 3 equal to 0. And we solve it. Thankfully, we know how to solve this one. We subtract 3 and then divide by 5 to get x is equal to negative 3 over 5. And that is not like a negative 3 over 5 comma 0, like a point. It is a vertical line. That is our vertical asymptote. Then in order to find the end behavior asymptotes, such as horizontal or vertical, which once again we're just concerning ourselves with, I said horizontal or vertical, horizontal or slant, but once again we're just concerning ourselves with the horizontal asymptotes, not the slant ones. So the degree of the numerator, so I'm just going to call that n, we said, is 0, because this has an x to the power of 0 secretly there. And the degree of the denominator is 1, because the x has a power of 1 on it. So this means that the degree of the numerator is less than the degree of the denominator, which according to what we just wrote a moment ago, tells us that, hey, there's a horizontal asymptote at y equals 0, plus or minus whatever translation is taking place. There is no translation vertically, so we just have the end behavior asymptote at y equals 0. On to the next one. There is a vertical asymptote here, and you find it by setting the denominator equals 0. So x equals 0. Well, we already solved that one. Then, in order to find the end behavior asymptotes, you find the degree of the numerator and the degree of the denominator. Degree of the numerator is 1, because x to the power of 1. Degree of the denominator is also 1. So when n is equal to d, when they have the same power, then you have the horizontal asymptote at y is equal to the leading coefficient. So what we have to do is the leading coefficient of the numerator and the leading coefficient of the denominator, and we divide. So we do 3 over 1, which would just be 3. Meaning our horizontal asymptote is at y equals 3. And once again, there would be plus or minus whatever translations over here, which there is none. So you just take 3 over this invisible 1, and that was our horizontal asymptote in this scenario. This last one, I want you to attempt it on your own. All right, so in order to find the vertical asymptote, we once again set the denominator equal to 0, so 2x minus 1 equals 0. To solve, we would add 1 and divide by 2, giving us x equal to 1/2. And that is not affected by any translations. Then, in order to find the end behavior asymptote, or asymptotes potentially, we look at the degree of the numerator and the degree of the denominator, both of which are 1. So we say, hey, they're equal to each other. So you have a horizontal asymptote at y equals the leading coefficients. So 1 divided by 2, aka 1/2. But we also have to add or subtract whatever translation's there. So it's being translated 4 down, so we also subtract 4. 1/2 minus 4 would give us y equals -3.5, or you could just call it -3.5, or if you really wanted to call it -7/2, you could. I prefer the decimal in this scenario because it'll be the most helpful number when graphing, because we can see -3.5 a little bit easier and a little bit quicker than -7/2. All right, so now some hints for graphing. Find the intercepts and asymptotes first. So we've practiced finding the asymptotes. In order to find the intercepts, once again, we just set the opposite value equal to 0. So whether it's x or y, set the other one equal to 0. Then make a table of values to discover the correct shape, and picking x values on each side of the vertical asymptotes. So you plug in points and get out the y's, plug in x's, get out y's. And then remember that arrows should be getting closer to your asymptotes, not necessarily farther away. And it's also a good hint here to use Desmos online graphing calculator, which you can find just by Googling Desmos, or some sort of other graphing utility, such as a graphing calculator, like Calc84 on your iPads. So in order to graph, on example 2 here, y equals 2x plus 1 over x minus 3, we'd say, hey, okay, let's find the x-intercepts. So in order to find the x-intercepts, we set y equal to 0. So we'd have 0 equals 2x plus 1 over x minus 3. Well, we don't like the fact that there is a variable in the denominator, so let's multiply both sides by x minus 3 over 1. That would reduce that, leaving us on the right with just 2x plus 1. On the left-hand side, we multiply by x minus 3, but we notice what's 0 times literally anything? Still 0. So conveniently enough, we don't have to worry about the denominator right now, because when you multiplied, it just turned to 0 on the left-hand side. So now we just solve this by subtracting 1 and then dividing by 2. So we get x is equal to -1/2. Now because this was an x-intercept, and because we did plug in y equal to 0, this is a point. So you get -1/2 comma 0. And I'm going to go ahead and graph that right there. Now, in order to find the y-intercept, I'm just going to draw a little line here to divide the two. I would say, okay, set x equal to 0. So 2 times 0 plus 1 over 0 minus 3. And now we solve. So 2 times 0 is 0, so you get 1 on the top. 0 minus 3 is -3. Y is equal to -1/3. And once again, because we did make an x value 0 here, or the x 0 I should note, then the point would be 0 comma -1/3, which we don't really care where the negative is. You can also call it -0.3 repeating if you'd like. So I'll go ahead and plot that right about there, knowing that, hey, the graph will go through those 2 points. In order to find the vertical asymptote, once again, we set the denominator equal to 0. So the denominator equal to 0 will be x minus 3 equals 0. Adding 3 to both sides gives you x equals 3. Meaning, x equals 3, you go 1, 2, 3 to the right. And you can just draw a dashed line through here. And what will happen is the graph will never touch that line. And then to find our end behavior asymptotes, we compare the degree of the numerator and the denominator. And they're both 1, so the degrees equal each other. So then you have a horizontal asymptote at y equals the leading coefficients, which is 2 divided by 1, aka 2, with no vertical translation up or down to worry about. So then at y equals 2, I'm going to draw my horizontal, or my end behavior asymptote, which is a horizontal asymptote in this scenario. Now to figure out, okay, well we have 2 points and we know where the graph doesn't touch, but it'll go near those asymptotes. But we don't know a lot of the graph still. So we're going to make an XY table, and I'm going to use the points 1, 4, and 5. And why I use these points is because 1 is on the left side of the vertical asymptote here, and we already have 2 other points on the left-hand side, whereas 4 and 5 are on the right-hand side of the asymptote, and we don't have any over there yet. So plugging these in, you can plug them in by hand or use your calculator at this point to compute the operation here of 2 times 1 plus 1 all divided by x, or 1 minus 3. And regardless of how you do it, you end up getting negative 1.5, whether it's negative 3 halves, negative 1.5, whatever. So I'm going to graph that. So 1 and negative 1.5. And then when you plug in 4, you end up getting 9. So I'm going to graph that. But notice it goes well off the graph, so I'm going to just kind of do my best. And then when you plug in 5, you end up getting 5.5, which still goes off the graph, but not by as much. So that kind of tells us as we connect our points that it's going to look something like this. Because once again, I knew it was going to come close to this over at the side and over here at the bottom. And on this one, I can see it going up, 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 up. And I know it's going to end up coming down there and getting close to this horizontal asymptote, but never touching it. And once again, using a graphing calculator such as Desmos or the Calc84 or the TI-84s you have in class are all incredibly helpful here in finding this graph shape. And you can also use it to find the table values as well. All right, so example 3. Go ahead and try as much of this one as you can on your own. Feeling free to go ahead or look back at the previous example to help you out. So in order to find the x-intercepts, we once again set the y value as 0. So we do 0 equals 5 over x minus 2. So before we add 2 in this scenario, or before we multiply by x in this scenario, we have to add 2. So we get 2 equals 5 over x. So then when we multiply by x over 1 on each side, it doesn't turn to 0 anymore. Instead, it becomes 2x equals 5, which we can notice there, oh, we divide by 2 to get x is 5 over 2, aka 2.5. So the x-intercept is 2.5. Once again, we plugged in 0 for y, so that's comma 0. So I graph that. In order to find the y-intercept, I make x 0. So we have y equals, let me go a little bit below this, y equals 5 over 0 minus 2. Well, you might notice, wait a second, you can't divide by 0. This is undefined. And it doesn't mean that it's just negative 2 then. It means that there is no y-intercept. Because it's not that you just can't, you just erase that and then go with minus 2. The entire thing's undefined because one part of it is being divided by 0. In order to find the vertical asymptotes, we set the denominator equal to 0. The denominator is just x, so x equals 0. And I'm going to go ahead and plot this vertical asymptote here at x equals 0, aka the y-axis. And the end behavior, we end up making it as, or comparing the degree of the numerator compared to the degree of the denominator. The numerator has a degree of 1, which is less than that of the denominator's degree of, the numerator has a degree of 0, which is less than that of the denominator's degree of 1. Because this doesn't even have an x, well, this has an x to the first. When this happens, then we have the horizontal asymptote at y equals 0, plus whatever translation we have, which is minus 2. Now I'm going to go ahead and plot that horizontal asymptote at y equals negative 2. So now we know the graph will never touch these points, but we'll get close to them. And then my x and y's, you can really pick whatever. This time I'm going to pick negative 5, negative 2, negative 1, and 1. And I picked those 3 negatives because I don't have anything over here. And I picked the one positive because I already have 1 point over here. You don't have to hit a certain number of points on each side necessarily, although it's a good idea to have anywhere from 2 to 3 at least. Negative 5 would give us negative 3, so I'll go ahead and plug that one in, or plot that I should say. Negative 2 gives us negative 4.5, so let me go ahead and plot that. And negative 1 gives you negative 7, which you would notice way down here. And so then we can see, oh, it's going to have some sort of curve like this. And then positive 1 gives you 3, telling you it's going to have some sort of curve, and we know it's just going to kind of be symmetrical with this curve, so it's going to go this way some way. some sort. All right, moving on to our next page, our last couple of graphing examples before moving to a more real life example here. So once again, try this one as much on your own as you can. So finding the x-intercepts, I'm going to make y 0. So I'm going to have 0 equals negative 4 over x plus 2 plus 3. First step would be subtracting the 3, getting negative 3 equals x, or pardon me, negative 4 over x plus 2. This time, as we multiply each side by x plus 2 over 1, or just x plus 2, whichever you prefer, it's the same thing. The right gives you negative 4 still, all the same. The left-hand side, they get to distribute, and you get negative 3x minus 6. So we'd solve by adding 6 and get negative 3x equals 2, dividing by 2 to get x equals negative 2/3, giving us a point, negative 2/3 comma 0, because once again, we made y 0. Plot it right about there. The y-intercept is found by making x 0, y equals negative 4 over 0 plus 2 plus 3. Well, 0 plus 2 is 2. Negative 4 divided by 2 is negative 2. Add 3 to it, and you get y equals 1. So you end up having the y-intercept 0, 1, because we did make x 0. The vertical asymptote is found by making the denominator equal to 0. X plus 2 equals 0 gives us x equals negative 2. So we know it'll never, ever, ever touch this vertical line. In the end behavior asymptote, we look at the degree of the numerator and denominator. Numerator has a degree of 0, which is less than that of the denominator with a degree of 1. So we say the graph will have a horizontal asymptote at y equals 0 plus whatever translation we have, which is 3. I don't even need the positive 3 there. So now I'm going to go to y equals 3 and put my horizontal asymptote, knowing that the graph will never touch it, but get close. Now I'm going to plot my x and my y's. And for this one, I'm choosing negative 5, negative 3, and 2. Once again, just points on this side of the graph and then another one on this side of the graph. I'm a little farther away than what I have. So negative 5 gives me 4.3, which would be right about there. Pardon me, right about there. Negative 3 ends up giving us 7, which, whoop, that's really high. Oh, and I apologize. Wait, no, never mind. I thought I put my my vertical asymptote at x equals negative 3, but I realized I did not. I put it in the correct spot at x equals negative 2. So never mind my whoopsie there. So x is negative 3, y is 7, clearly going off the graph. And so it's going to look something like this. And we still have a lot of other space to work with here on this graph, given that it's only a 5 by 5 graph, or 10 by 10 really, going 10 this way and 10 this way. And then 2 gives us 2. So go ahead and plot that. And that gives a little more shape to this, knowing it'll kind of look like this. And once again, using a graphing utility such as Desmos or Graphing Calculator will help greatly with this. On to example 5, go and try this one to the best of your abilities. X-intercept, once again, we make y equal to 0. So you have 0 equals negative 3x plus 2 over negative x minus 1. I'm excited when I see this because once again, when I multiply by the denominator here over 1, I notice the left-hand side is equal to 0 at this point because I didn't have any translation, meaning it's going to be 0 equals negative 3x plus 2, making this problem a little bit easier. So then we end up subtracting 2. Whoa, I'm not sure what happened there. How did I find this zone? Subtracting 2 to get negative 2 equals negative 3x. Dividing by negative 3 gives you x equals 2/3, or 0.6 repeating. So the x-intercept is 2/3, 0, because once again we made the y value 0, plotting that right about there. Then we make the x equal to 0, and we get y equals negative 3 times 0 plus 2 over negative 0 minus 1. Now, you're saying, Mr. Crossell, if I know that negative 3 times 0 is just going to be 0, and plugging in 0 on the bottom is just going to give me negative 1, do I have to write all of this out? No, you definitely don't. Write only what you need. So if you can notice, hey, this can be -2. Great. If you need to go through the step and do 0 plus 2 is 2, -0 minus 1 is -1, and then go from that and say, oh, it's -2. That's also fine. So we end up getting -2 as our y, and 0 was our x because we plugged it in. So we have 0, comma, -2. Vertical asymptote, once again, you set your denominator equal to 0, which is -x minus 1 equals 0. So you get -x, or I'm just going to actually add x in this scenario to save myself a step. -1 equals x. If you added the 1, you'd have to divide or multiply by -1, which would give you the same answer. So plotting that, knowing that the graph will never ever touch but get close to this vertical asymptote. The end behavior asymptote, both the numerator and denominator have a degree of 1, x to the first and x to the first. And so when that happens, you have the end behavior asymptote is the leading coefficients, and plus or minus whatever translation there is, and it's -3 divided by -1, which is just y equals 3. So now my x and my y's, in order to help me out a bit with the graph, I'm going to put in -5 and -2. I'm going to say, hey, sure, I'm content here. If you wanted to, you can plug in, 2, 3, 4, or 5 here. Those would all be good values to plug in as well. I'm choosing not to this time, for really no rhyme or reason, other than that, hey, I already know on my graphing utility what it'll look like. So plotting these points gives you a look about there. And looking on your graphing calculator tells you, oh, it'll be about this. But you can also plug in those points to get a better and more accurate look. On to more of the real life examples, word problems. So to join a rock climbing gym, you must pay an initial fee of $100 and a monthly fee of $59. Yikes, gym fees are the worst. Write an equation that gives the average cost per month as a function of the number of months of the membership. So I hope it makes sense to you, but if not, let me help explain it a bit, that over time, this becomes cheaper and cheaper and cheaper on average, because the first month is going to be the most expensive because you spend $159 for that 1 month because you have the initial fee plus that monthly fee. But over 2 months, then you've now paid 100 plus 59 plus 59, giving you 218 over 2 months, which instead of 159 for 1 month is now 109 for 2 months, which is $50 cheaper per month, quote unquote. So then if you have 3 months, then you add another 59 to the top and divide the number by 3, getting it even cheaper and cheaper and cheaper. So over time, you end up paying less per month, getting much closer to that $59 monthly fee on average. So in order to find a function for this, let's first state what our variable is. So we want to find out the number of months. So x is going to be that number of months. And let's first find an equation just for how much you pay. Well, f of x is equal to $100 initially plus $59 per month. And you could, of course, add those in either order. Oh man, I'm trying to fix my 5 and it just keeps getting worse. I'll say that's slightly less bad. So now, in order to find it as an average per month, for how many months you have, well, in order to find averages, we divide by how many there are. So we divide by the number of months. Well, the number of months is ever changing, and we called it x. So that would give us our function here. So you take 100 plus $59 per month you are a member, and divide it by the number of months that you're a member. So graph on your calculator, that should be your calculator, and determine how many months it'll take for the average cost to be $69. So what you would do is you would first graph this function, being careful to type the top in parentheses there so your calculator knows that all goes in the numerator. And then the other thing you do is you graph y equals 69, and you find the intersection of these two functions. Because if the x value is the number of months, that means the y value is going to be the amount of money. So I turned my graphing utility here, calc84. And if you look at my y equals, I did type in these functions. And I'm going to go and graph. And as you graph, you probably start out down here. So I zoomed out quite a bit already by hitting zoom and zoom out, zoom out, zoom out. And then I moved up to where I could see where these would intersect, knowing that y equals 69 would be, well, when y is 69. And knowing that I'd find the x value around there somewhere. So I have to figure out, okay, well, what is the x value here? Well, I'm going to hit intersect, and it tells me right there. On the graphing calculator, you have to actually hit, or on the TI-84s, you actually have to go in and push to find the intersection like we have previously. And if you're in class, I will show you how to do that in class. And if you're not in class, come back and see me outside of class time, and I will gladly help you with that. So we can see here the X value is 10, so it takes 10 months to get an average monthly cost of $69. So 10 months is the answer. And that is it for section 1 of Unit 10.